Good morning. This is the final part of the alkalinity videos. In this one, we're focusing on MATLAB for alkalinity. So we're going to be talking about how we use that MATLAB code to generate the data analysis that we need. To do this, first we're going to talk about the samples. We have a sample ID for each sample. The first sample was the borax sample. One thing I wanted to point out about the borax sample is that borax is actually a combination of both the acid and the base. Since there are 4 boron molecules in borax, we actually create 0.02 moles per liter of BOH3, the acid, and 0.02 moles per liter of BOH4 minus the base. So if we add the acid and the base, our expectation is that our titration would actually start at the pKa. Remember, if you add equal amounts of acid and base, you end up at the pKa. This is accounted for in the MATLAB code. Second sample was the sodium carbonate. Sodium carbonate is a diprotic acid, so it should have 2 equivalence points, where in the first case we titrate the carbonate to bicarbonate, or HCO3 minus, and as we continue the titration, we will reach the second equivalence point, which is where we have converted the bicarbonate that we formed to carbonic acid. The third sample is sodium hydroxide, our strong base. The fourth sample was Austin tap water. Fifth, distilled water. Sixth, Lake Austin water. And seventh, Waller Creek, a sample from Eastwoods Park. I should say that the first 3 samples are what we refer to as our known samples. So I'll point that out as well. Okay, so within Canvas, we've put a zip file that contains a number of files within it. The first 2 are data files. Alkalinity class data contains the data for each of the titrations that we've selected for analysis. The second file contains the initial pH associated with each of those. Both of these files are needed and you need to read them in. We'll talk about that in a bit. And the main program is called alkalinity student final.m. This MATLAB code calls all of the other functions and essentially subroutines, if you will, and creates the tables and plots that you need. So the 3 functions, the titration plot, alk.m, creates the theoretical titrations curves for the first 3 samples. The inflection points.m is a curve fitting routine which fits the data and then takes the derivative of those curves to find the inflection points. Match-inflection.m then locates the data points corresponding to the expected inflection points. And so that's how we identify the endpoints of our titration. I should say the equivalent points of our titration. It will also match. We will also do matching to get the color endpoints to match as well. And we'll see that as we go. So the code has 4 goals. It has a number of goals which will end up producing 4 tables and 10 plots for you. The first is to read and import the lab data, create a table of initial data that will allow you to see what the initial pH of the data was for each of the samples. There's then a loop that is used to calculate for each of the samples the equivalence of strong acid at each step, and it allows you to find the pH and associated equivalents of strong acid added at the inflection points and at the endpoints where we saw a color change. And then that also creates summary tables. Then finally, it will compare the theoretical titration curves with the actual titration curves for the known samples and create a summary table that shows you the error between what we actually collected in the lab data and what we expected based on what we initially added in samples 1 through 3. Okay. So, once that's done, we also obtain plots. So for each of the samples, we obtain plots for that has the data on it, the fitted curves, the inflection points determined from the derivatives, and the color change. In addition, another 3 plots are created that compare the theoretical titration curves with the actual titration curves for the known samples, for a total of 10 plots. Let's take a look at the code to see if we can identify these tasks. So there's a description of the code up front. This is the main point, the main code, alkalinity student final. As we scroll down, you'll notice, and this will be summarized for you in another slide, you're going to input the sample volume. Sliding down further, this is the section where we're reading and importing the potentiometric and indicator data. So you need to put in the data that you're inputting in here, and so you need a read statement, and then also the initial data file as well as all of the data. Okay, so 2 different data files that you're reading from, which are indicated as the alkalinity class data text and the initial pH data text files. The next thing is to generate the table of initial pH values. So you notice the sample names are already added for you. You can see that the sample names correspond to the IDs that were in the table from the PowerPoint. Then calculate the mean and standard deviation for the samples so that we can see what the initial data variability looked like in terms of pH. Okay, on line 71, we're moving on to data analysis. Okay. So here's where we're calculating the equivalents per liter added. And again, you're asked to provide that calculation. Make sure you look at the headers in the data file in alkalinity class data.txt so you know what variables you're using in this calculation. This next step, it basically is to identify so that we can summarize whether the inflection point that you find is associated with carbonate equilibrium or the carbonate alkalinity or the total alkalinity. So the carbonate alkalinity, remember, is the inflection point that will occur about pH 8.3. And the total alkalinity is the one that's inflection point that is around 4.3, pH of 4.3. Okay? So our summary tables will basically indicate whether we're looking at carbonate or total alkalinity based on that pH and the indicator. Okay. Next thing we're doing is basically starting to our for loop. So here's the for loop where we're going to analyze each data set independently. We've, remember, already calculated the equivalents per liter added for each sample, and we're going to use that data to go in and find the inflection points using the inflection points function that we've created. Then we're going to match the inflection point to find the points closest to theoretical points, identify whether those are associated with carbonate and total. So this is where we are trying to determine where the inflection points are. We're fitting the data, and finding the derivatives to get the inflection points. Okay, we're then going to add that data to our file. so that we can put all this together. And we're going to locate where the indicator changes color as well and add that to the color data file. Okay. We're then going to make the plot associated with the titration data and the fit and indicate where the inflection points and color changes occurred. Then we're going to move down and do the calculations for the three known samples, starting with the borax. You have to add the pKa's, the standard normality of the titrant. So what did the standardized normality of the titrant. So what was our titrant concentration? And that's in the data file, so you can look for it there. And then what was our sample volume? We do the next for after we plot that data, and this is the plotting component of that. We do the same thing for the sodium carbonate. So again, you're going to add the pKa's, the normality of the titrant, the hydrochloric acid in our case. Add the sample volume, and again, create that plot. Then we're going to add the sodium hydroxide, or do the same thing for the sodium hydroxide. Again, adding the pKa's, the normality of the titrant, and the sample volume, and create the plot for the theoretical and actual experimental titration data. Then finally, we're going to convert our alkalinity from equivalents to liter to milligrams per liter as calcium carbonate for both the titrate for the alkalinities determined from the inflection points in the potentiometric titration data and for the color changes. And that's the end of the data analysis section. Finally then, the last step was to look at the molarities of the samples, 0.01 molar for the borax, 0.01 molar for the sodium carbonate, and 0.02 molar for the sodium hydroxide. And we're going to compare whether we obtain those molarities using the titration curves that we obtained experimentally and finding the inflection points and comparing those. So that will give us the ability to create a summary that allows us to look at the error. So just scrolling down to let you see what some of the tables look like. After I ran this, you can see here is the summary of the samples with their initial data. The number of samples are shown, the mean of the pH, and the standard deviation of pH among the samples. Okay. The results that summarize where the alkalinity was determined using the indicator colors is the next table, and you can see that the samples are ID'd by their number. Here's the sample name, which group it came from, the equivalents per liter that were added to get to that endpoint or equivalence point. In this case, this was based on the color change results. So for the color change results, you can see what the alkalinity was for each of our samples, whether it was the carbonate alkalinity, which corresponded to the first color change for the phenolphthalein, or the total that corresponded to the color change for the methyl orange. And then finally you see all the samples. The third table that gets created includes the samples for the alkalinity determined from the inflection points of the titration. And again, you can see the milliliters of acid added, what pH the inflection point was found at, what the alkalinity was calculated, and then it's converted to milligrams per liter as calcium carbonate as well. So all of this data is generated for you. And finally, the last table is the table that shows the sample name, what the molarity was that was determined from the sample, and then the error that was associated with comparing that to the theoretical value, or the value that was associated with what we added to the solution. A typical plot looks like this. You can see this is, well, whoops, that's the theoretical curve. Let's see, there we go. This is the sodium carbonate curve. You can see the data that you collected, the fitted curve, okay? And you can see the location where the colors changed and where the derivatives were found using the inflection point .m function. Okay, so notice in this case it's kind of cool. We get the color change and the derivative at the same location. Here it's a little bit off. So that's the type of output that you get for the for the samples. And again, you get that data, and then the other type of plot that you're going to see is a plot that compares the theoretical titration curve in the line and your data. You can see it matches up pretty well. So that's the data that we get. Going back to the PowerPoint presentation, again, these are what the file does for you. Here's what you need to take a look at. This is an example of a few of the samples taken out of alkalinity class data.txt. You can see what that data looks like. You can see the normality of the titrant that we were trying for. When we standardize it, this is what we actually got. This was the milliliters associated with getting to the color changes, and you can see here is the 0 indicates that we're not at any of the indicator points, so this is just a typical data point. This specific data point shows that this is where the first color change occurred. This is where the indicator changed, occurred at pH 8.03, and the second color change occurred at pH 3.06. So this is just some typical data from that file. The initial pH data.txt file contains, again, the section and group numbers and sample IDs. Again, this is the normality of the titrant that we were aiming for. This will have milliliters of 0 because we haven't added anything yet. And you'll notice that for sample ID number 1, the borax, the pH comes out to be about 9.25, which is very close to the pKa for the boric acid system. And as I indicated, by adding borax, we're adding equal amounts of the acid and the base. The second thing you'll notice is I put here 2 samples for sample 6, and you'll notice how close the initial pH came. That's a good sign. Some of the other data wasn't quite as close. So this is what the data looks like. And then next, what I would show is your MATLAB task. So I identified all of the line numbers where you need to do some work. Line 32, you're going to input the sample data. 41 and 45, you're reading the data. It's line 77, you're going to create an equation for calculating the equivalence per liter added. And then you're going to add the pKa's, the normality of the titrant. You want to add the actual value, the sample volume, neglecting the titrant, volume added, and then the equations for milligrams per liter as calcium carbonate for the alkalinity determined from the inflection points, and the same thing for the alkalinity determined from the color change data of the indicators. Essential data slides. Now, this is what you need to make sure is included in your presentation, along with your introduction and methods and other conclusions that you may want to make. First, you need the pH summary table that has the initial sample data. Again, this is created for you. The plots of the titration that contains the dated, the fitted data, the date or color change and where the slope changed. And those are figures 1, 3, 5, 7 through 10. And then a summary of the alkalinity determined from the inflection points and indicators. So these are the tables that were created. Make sure you put in your sample calculations. Make sure you put in a summary of the concentrations determined from the known samples and error. So that's the QC summary table. And then when answering the questions, prepare discussion slides that respond to those questions. These can be multiple slides depending on your answer. And if there's a plot that would back up your statement, include that. For example, figures 2, 4, and 6 would be good for question 1, which is asking how the theoretical and actual titrations compared for the known samples. So I think that's about it. I hope this helps. Please feel free to text us, email us, or give us a call if you have questions. And have a great weekend. Take care.